Sketch the graph of the function f of x equals 12x minus 36 divided by x cubed minus 3x squared plus 3x minus 9 by determining the parts a through I. F of x equals 12x minus 36 divided by x cubed minus 3x squared plus 3x minus 9. So f of x has a denominator, and both the numerator and the denominator can be factored here. The numerator has a common factor of a 12. Factoring it out will leave behind an x minus 3. The denominator is a 4-term cubic. We can attempt to factor it by group factoring. If we group together the first two terms, they have a common factor of x squared. Factoring out the x squared will leave behind an x minus 3. Grouping together the second two terms, they have a common factor of positive 3. Factoring that out will leave behind also an x minus 3. Since the x minus 3 factors match, group factoring is possible. Leaving the numerator alone, in the denominator we can factor out the common factor of x minus 3. Factoring it out will leave behind an x squared plus 3. X squared plus 3 is a sum of squares and does not further factor. The domain requires that the denominator cannot equal to 0. So x minus 3 times x squared plus 3 cannot equal to 0 here. Since it's factored, we can solve for the values that x cannot be. The x minus 3 factor gives that x cannot be a positive 3, and the x squared plus 3 factor gives that x squared cannot equal negative 3. Solving for x by taking the square root of both sides, x cannot equal plus or minus the square root of negative 3, which is an even root of a negative number, which is a non-real number. The only real number that x cannot be is a positive 3. So for part A, the domain will be all real numbers except positive 3. It'll be all real numbers to the left of positive 3, negative infinity up to positive 3, not including it, round bracket. Union, all real numbers to the right of positive 3, not including it, round bracket, up to positive infinity. Another thing about the function f of x, it has a factor in the numerator that fully cancels with the factor in the denominator, which indicates that there will be a hole in the graph where x minus 3 equals 0, x equals positive 3. Other than that, we can work with the remaining portion of the function, which is 12 divided by x squared plus 3. For part B, we want to determine if there is any symmetry. This is done by evaluating f of negative x and comparing it to the original function f of x. F of x is made up of, in the canceled version, in the denominator, an even power of x, which will have y-axis or even symmetry, added to a constant, which always has y-axis or even symmetry. Since the two match, the denominator will have y-axis or even symmetry. The numerator is a constant, which always has y-axis or even symmetry. And even divided by an even, since they match in its division, is an even. So f of x will have y-axis or even symmetry, except because of the x minus 3 factor canceling, it will have a hole at x equals positive 3 that is not part of the symmetry. F of negative x is 12 divided by negative x squared plus 3. And negative squared is a positive, x squared plus 3. Comparing this result to the original, it is exactly the same as the original, except for the x minus 3 factor that is canceled. So f of negative x equals f of x, which is the exact condition needed to have y-axis, also known as even symmetry, which means that the graph will be its own mirror image over the y-axis, except for the fact that we have determined there is a hole at x equals positive 3, which will not show the symmetry because there is not a hole at x equals negative 3 symmetric over the y-axis. Other than that, the graph will have the y-axis or even symmetry. For part C, we want to determine the y-intercept. This is the point where the graph crosses the y-axis, defined by x equals 0. We can find the corresponding y-coordinate by plugging the x-coordinate 0 back into the original function, y equals f of 0. We can use the canceled version, which will be 12 over 0 squared plus 3. 0 squared is 0, plus 3 is 3. 12 divided by 3 is a 4. We had an x-coordinate of 0, we found a corresponding y-coordinate of 4. For part D, we want to determine the x-intercepts. These are the points where the graph crosses the x-axis, defined by y equals 0. Y, which is f of x, is going to be set equal to 0, and we want to solve for all x's. We will use the version of the function after all factors have canceled from the numerator and the denominator. Y, which is f of x, will be set to be 0 and set equal to just the numerator. And we want to solve for all x's. There are no x's, and 0 and 12 do not equal to each other. So for x-intercepts, there are none. For part E, we want to determine any vertical asymptotes. This is done by taking the denominator after all factors have been canceled from the numerator and denominator. The remaining denominator, which is x squared plus 3, is set equal to 0 and solve for x's. X squared equals negative 3. X equals plus or minus the square root of negative 3, which is an even root of a negative number, which is a non-real result. So for vertical asymptotes, there will be none. For part F, we want to determine if there are any holes in the graph. We had an x minus 3 factor that fully canceled with the factor in the denominator. If we take that factor and set it equal to 0 and solve for x, that will be the x-coordinate of the hole. If we have an x-coordinate of 3, we can find the corresponding y-coordinate by plugging the x-coordinate back into the original function, so y equals f of 3. We can use the canceled version of the function, which is 12 over 3 squared plus 3. 3 squared is a 9 plus 3. 9 plus 3 is 12. 12 divided by 12 is a 1. We had an x-coordinate of 3. We found a corresponding y-coordinate of 1. There's where the hole is located. For part G, we want to determine the end behavior, horizontal asymptotes or slant asymptotes. F of x, in its canceled version, is a constant in the numerator, which is a power 0, divided by a polynomial whose highest power term is power 2. Since the power in the denominator is greater than or equal to the numerator, there will be a horizontal asymptote. Since the power in the denominator is strictly greater than the numerator, the horizontal asymptote will be y equals 0. The horizontal asymptote can be determined by setting y equal to the limit as x approaches positive or negative infinity. They will match here because f of x is a polynomial over another polynomial. We can use the version after canceling, so 12 divided by x squared plus 3. Plugging in positive or negative infinity for the x in the denominator, squaring it will be positive infinity, plus 3 will be positive infinity, and 12 divided by positive infinity will be a 0. So y equals 0 will be the horizontal asymptote. For part H, we want to determine the intervals of trend, relative maxima, relative minima, plateaus, and cliffs. All of this will involve the first derivative, f prime of x. We can take the first derivative from the canceled version of f of x. We will need a little bit of room for this, so we can work this out on another page. The canceled version of f of x is 12 divided by x squared plus 3. So it is a fraction, but no quotient rule is needed since the numerator does not have an x at all. It is just a constant. We can rewrite f of x by bringing the x squared plus 3 to the numerator as a negative first power, and only a power rule with a chain rule is needed for the first derivative. F prime of x will equal, bring down the power and multiply with the 12, negative 12. Leave the inside alone, x squared plus 3, subtract 1 from the power, negative 2 power, and then multiply by the derivative of the inside to complete the chain rule. We can put the constants together, negative 12 times 2, which is a negative 24. We have an x, and we have an x squared plus 3 to the negative 2 power. We want all powers to be positive, so we will move the negative 2 power, the negative 24 and the x will stay in the numerator, and the x squared plus 3 will move to the denominator to become a positive 2 power. We want to fully factor the first derivative. The numerator is a single term, which never factors, and the denominator is a sum of squares, which also never factors. So this is the fully factored version of the first derivative. This is the one we're going to want. So f prime of x equals negative 24x divided by x squared plus 3 squared. We have the first derivative written as a single fraction. All powers are positive, and it is fully factored. So we can set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. From the numerator, if we divide both sides by negative 24, we get x equals 0. From the denominator, we need x squared plus 3 to equal 0. We can subtract 3 from both sides, so x squared equals negative 3. Take the square root of both sides, x will equal plus or minus the square root of negative 3, which is an even root of a negative number, which is a non-real number. We'll now check to see which of these are in the domain. The domain is all real numbers except for positive 3. X equals 0 is a real number, and it is not positive 3, so it is in the domain, and it is a critical number. X equals plus or minus the square root of negative 3 are non-real numbers. They are therefore not in the domain. We can cross them out. They are not critical numbers. We can now draw a domain line, a line representing the domain. It has no left end because it begins at negative infinity, and it has no right end because it ends at positive infinity. It does not include 3 because x equals 3 was determined to be a hole in the graph. So the domain is already split into two separate intervals. We can put any critical numbers on here in order. 0 will be to the left of 3, which further splits the domain into what is now 3 separate intervals. We can pick a test value in each of the intervals. The first interval, negative infinity to 0, we can pick negative 10. The next interval, 0 to 3, we can pick 1. The next interval, 3 to positive infinity, we can pick positive 10. And we can test the trend by plugging the test values into the first derivative. We only care whether it is positive or negative. So the best place to plug in is the fully factored version. That is the version that is right here. A couple things about this. In the denominator, x squared is always positive unless x is a 0, in which case it's a 0. But then when it's added to the 3, it's guaranteed positive. And then it's squared. So that entire denominator is positive and will not determine whether the first derivative is positive or negative. Only the numerator matters. And we will be sure to account for the negative 24 as part of the numerator. Plugging in the test value of negative 10, negative 24 times negative 10, negative times negative is a positive. We have a positive first derivative. This corresponds to an increasing trend. Plugging the test value of 1 into the portion of the first derivative that matters, negative 24 times positive 1, negative times positive is negative. We have a negative first derivative, which corresponds to a decreasing trend. Plugging the test value of positive 10 into the portion of the first derivative that matters, negative 24 times positive 10, negative times positive is negative. We have a negative first derivative, which corresponds to a decreasing trend. Right at the critical number of x equals 0, we have the trend change from increasing to decreasing, so x equals 0 will be a relative maximum. X equals 0 came from the numerator, so it will be a normal relative maximum. It has an x-coordinate of 0, and it has a y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of 0. We can use the cancel version, so this will be 12 over 0 squared plus 3, which is 12 over 0 squared is 0 plus 3 is 3, and 12 divided by 3 is a 4. We have a corresponding y-coordinate of 4. X equals 3 is not a critical number. It's a hole in the graph, and the graph on each side will be decreasing, and it will connect together in one continuous decreasing other than the hole at x equals 3. For part I, we want to determine the intervals of concavity and any inflection points. All of this involves the second derivative, f double prime of x. We'll take this from the first derivative. It will require a little more room. We can work this out on the other page. F double prime of x equals, we have two options. We can use this version of the first derivative, in which case it'll be a product rule, or we can use this version of the first derivative, in which case it'll be a quotient rule. I'll use the quotient rule version. The derivative of the numerator, which is a negative 24, times the denominator left alone, x squared plus 3 squared, minus the numerator left alone, negative 24x, times the derivative of the denominator, which is a power rule. Bring the power down, leave the inside alone, subtract 1 from the power, it'll be to the first power now, and then multiply by the derivative of the inside to complete the chain rule. All of this will be over the denominator squared. In the numerator, we have a negative 24. We have an x squared plus 3 squared for the first term. We will leave it alone. For the second term, we can collect all the constants together. We have a negative implied 1, a negative 24, a 2, and a 2. Negative 1 times negative 24 is positive 24, times a 2 is positive 48, times another 2 is a positive 96. We have an x and another x, so x squared. And we have an x squared plus 3. All this is over x squared plus 3 squared and then squared again, in which case we multiply the exponents. 2 times 2 is a 4. As a rule of thumb, the power in the denominator should increase by 1 for every successive derivative. Comparing the power in the denominator for the second derivative to the power in the denominator for the first derivative, it appears to have increased by 2. It should only increase by 1, and that's because in the numerator we actually have a common factor of an x squared plus 3 in each term, and it will factor out and be able to cancel the power in the denominator down. That's a nice way to check to see if the result of the second derivative is possibly correct. We want to fully factor the second derivative. There is a common factor from the constants of negative 24 and positive 96. 96 is divisible by 24, so we can factor out a 24. And we can factor out a power of x squared plus 3. The lower of the two powers, we have a 2 and a 1. The lower power is the 1. So we can factor out x squared plus 3 to the first power. Factoring out the 24, we'll leave a negative 1 here and a positive 4 here. Factoring out the x squared plus 3 to the first power, factoring is division, division is subtraction of exponents, we'll subtract a 1 from each of the powers. 2 minus 1 is 1, we'll have that to the first power. And this power here is a 1, it's an implied 1. Subtracting 1 from it will be a 0, and anything raised to 0 is a 1. So we have left a negative 1 times x squared plus 3 plus 4 times x squared. There's what is left over after factoring. So we have a negative implied 1 times x squared plus 3, and then plus a 4 x squared. All of this is divided by x squared plus 3 to the fourth power. We can now cancel the 1 power in the numerator with one of them in the denominator. It will now be to the power of 3, which is the 1 higher in the denominator as expected from the first derivative. So f double prime of x equals, we have a 24. Inside of the square brackets, we can distribute the minus 1 in here, which will be a negative x squared minus 3. And then we have the plus 4x squared. Over the denominator, x squared plus 3 cubed. So we have 24 times, we can combine like terms together in the square brackets and turn them into parentheses. Negative 1x squared plus 4x squared will be a 3x squared. We have a minus 3. And then over the denominator. We want to fully factor the second derivative. In the numerator, there's a common factor of 3. Factoring it out, 3 times 24 will become a 72. Factoring out will leave behind a 1x squared minus 1. The denominator is a sum of squares and does not further factor, so we will leave it as is. In the numerator, we have a difference of squares which factors into x plus 1 and x minus 1. And we will leave the denominator as is. There is the version of the second derivative we're going to want. So it came out to 72 times x plus 1 times x minus 1 divided by x squared plus 3 cubed. We have the second derivative written as a single fraction. It is fully factored. All powers are positive. So we can set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. From the numerator, since it is fully factored, the x plus 1 factor will give x equals negative 1, and the x minus 1 factor will give x equals positive 1. From the denominator, we get that x squared plus 3 needs to equal 0, which means that x squared needs to equal negative 3. Taking the square root of both sides, x will equal plus or minus the square root of negative 3. Again, we're getting an even root of a negative number, which is a non-real number. The domain is all real numbers except for positive 3. We want to check to see which of these are in the domain. X equals negative 1 and x equals positive 1 are real numbers, and they are not a positive 3, so they are in the domain. And they are both candidate numbers. X equals plus or minus the even root of a negative number, which are non-real numbers, are not in the domain, and we will cross them out. We can now draw a domain line representing the domain. It has no left end, it begins at negative infinity. It has no right end, it ends at positive infinity. It does not include 3 because 3 is a hole in the graph. And we can put all remaining candidate numbers on here in order. We have a -1 and then a +1, which splits the domain interval, which was already in 2 intervals, into what is now 4 separate intervals. We can pick a test value in each of the intervals. The first interval, -∞ to -1, we can pick -10. The next interval, -1 to +1, we can pick 0. The next interval, +1 to +3, we can pick 2. And the next interval, +3 to +∞, we can pick +10. We can test the concavity by plugging the test values into the second derivative. We only care whether it's positive or negative, so the best place to plug in is the fully factored version. That is this one here. A couple things about this. In the denominator, x squared is always positive, unless x is 0, in which case it's a 0. But then it's added a 3, so it's guaranteed positive, and then cubed is guaranteed positive. The entire denominator is positive and will therefore not affect whether the second derivative is positive or negative. In the numerator, the 72 is positive and will also not affect whether the second derivative is positive or negative. So the only portion of the second derivative that matters is the x plus 1 times the x minus 1. Those can be positive or negative depending on the value of x. Plugging in the test value of -10 to the portion of the second derivative that matters, -10 plus 1 is negative, -10 minus 1 is negative, negative times negative is positive. We have a positive second derivative, which corresponds to concave up. Plugging a test value of 0 into the portion of the second derivative that matters, 0 plus 1 is positive, 0 minus 1 is negative. Positive times negative is negative. We have a negative second derivative, which corresponds to concave down. Plugging the test value of +2 into the portion of the second derivative that matters, 2 plus 1 is positive, 2 minus 1 is positive, positive times positive is positive. We have a positive second derivative, which corresponds to concave up. And plug in a test value of 10 to the portion of the second derivative that matters. 10 plus 1 is positive, 10 minus 1 is positive, positive times positive is positive. We have a positive second derivative, which corresponds to concave up. Right at the candidate number of x equals -1, we have the concavity changing from concave up to concave down. So x equals -1 will be an inflection point. It has an x-coordinate of -1. It has a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of -1. We can use the canceled version, which will be 12 divided by -1 squared plus 3. -1 squared is a +1 plus 3. And 1 plus 3 is a 4. 12 divided by a 4 will be a 3, so it has a corresponding y-coordinate of 3. Right at the candidate number of x equals +1, we have the concavity changing from concave down to concave up. So x equals +1 will also be an inflection point. It has an x-coordinate of +1. It has a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of +1. We can use the canceled version again, so this will be 12 divided by 1 squared plus 3. One squared is 1 plus 3. And 1 plus 3 is a 4. 12 divided by a 4 is a 3. We have a corresponding y-coordinate of 3. We can now draw the graph. We have a vertical axis. We have a horizontal axis. We have a domain that is all real numbers except for +3. And +3 ended up being a hole in the graph. We have y-axis or even symmetry for the entire graph, which means it'll be its own mirror image over the y-axis, except the whole will not follow this. We'll be sure that that is the case. We have a y-intercept at 0, 4. We can graph that at 0, 4. That will be about right here. And we can label it. We have no x-intercepts. We will be sure that it does not cross the x-axis. We have no vertical asymptotes. We do have a hole in the graph at 3, 1. That'll be somewhere about right here. This is the one point that is not showing the symmetry over the y-axis. And what that means is that we will have at the symmetric portion over the y-axis to this point, which will be a negative 3, 1, the point that's over here. It'll be about the same distance away from the y-axis, but on the other side, we will have what will not be a hole in the graph. And that is the one point that does not show the y-axis or even symmetry. The rest of the graph will. We have that the point 0, 4 is a normal relative maximum. So we'll give it a normal relative maximum kind of shape. Something like so. We have an inflection point at negative 1, 3. So that'll be somewhere about right here, where the concavity on the left of it is concave up, so it'll start to be concave up, and on the right of it will be concave down, so it'll start becoming concave down there. And we can label that point as negative 1, 3. And we also have an inflection point at 1, 3. That'll be about right here. We can label that as 1, 3. On the left of it, it is concave down. That'll be over here, so it should be concave down there. And then it starts to become concave up. Concave up will be curving upwards, so we'll be sure that it's doing that. And we have a horizontal asymptote of y equals 0, which is the x-axis that we need to follow. So the x-axis, we can put a dashed line. We have this horizontal asymptote. And so it'll have behavior of approaching that horizontal asymptote. We had no x-intercepts here, so it will never cross the x-axis. So it can only approach towards this horizontal asymptote and never cross it. For the portion that is to the left of the negative 1, 3 inflection point, we have it's concave up, it's increasing, it passes through this symmetric point to the hole in the graph, and it has to be approaching the horizontal asymptote as x approaches negative infinity. All of that together tells us it'll have a shape of approaching the asymptote, passing through this point, increasing, remaining concave up. So it'll look like that. To the right of the inflection point of 1, 3, we have it remaining concave up, and it's actually going to stay concave up through and across the hole, except it does not include the hole. And it is decreasing, and it has to approach the horizontal asymptote as x approaches positive infinity, Again, there is no x-intercepts. It cannot cross it. So that together indicates that it will pass through, but does not include the hole and approach to the horizontal asymptote. So we have the domain is all real numbers except for 3, and we can see why the 3 isn't included. It's the hole in the graph. And the graph is showing symmetry over the y-axis, also known as even symmetry, except the hole. And the hole symmetric point is here, and it is not a hole, it's an included point. So it is not showing the symmetry as expected. Everything is checking out here. This will therefore be the graph of f of x.